Hello friends, welcome to my channel. Today we'll discuss about ownership and borrowing. Now let's start with one example with demonstrating that stack and heap memory. By default, as we know that integers, character, floating point numbers are stored in a stack memory. But box will allow us to allocate the memory inside heap and returns a pointer. And as soon as this main function is completed, the memory allocated in heap will be freed. Similarly, we can define another box variable inside a inner scope, and as soon as this inner scope is exited or completed, the memory allocated in heap by box2 variable will be freed. And using star box1 and star box2, we can retrieve that values which is stored inside box1 and box2. The star is known as dereferenced operator, and similar to inner scope, we can allocate a memory inside function. So whenever this function call is completed, at that time that memory allocated by this box1 will be freed as well. Let's define a structure of point with two x and y, because x and y are floating point numbers. So this memory will be allocated in a stack memory. So we can create an instance p which with a value x and y, and this is the structure of it. And as soon as this main function is completed, the memory allocated either in stack or heap, wherever it is, it will be freed or it will be deallocated. And there is a trait known as drop. Drop, if you implement the functionality provided by drop, which will allow us to provide some cleanup operation. Now let's implement of it. So this is a trait drop. We implement for point struct, and it has its drop function which take the mutable reference, and inside this function it will provide an opportunity to do any cleanup resources and cleanup logic before the memory allocated for this p instance is complete freed. So it won't stop us for reallocating the memory. It won't interfere with the allocation or deallocation, but it will allow us to provide some functionality before we clean up the memory. Now talk about ownership. And one important thing to remember, ownership is mostly applied to the variable represented to a heap allocated memory. Because if the primitive types, for example, integer, floating point numbers, if you are using that, the ownership concept doesn't arise there, because the value will be copied from one stack location to another. Now let's see what I mean. So I define a variable x with 45 values, and this is a simple operation. I assign y equal to x, and I can print x and y later. That means in this line, the value of x is copied to here. Now x and y both represented to a stack location which contain 45 values in each places. So along the program we can use x and y. There is no ownership concept involved, because this x is a primitive value which store a unsigned integer data and which contains 45 values. So both will contain 45, the data will be copied. But if you represent along with box, and we store some integer data, but box allocate not in stack, rather in a heap. So if you assign like to another variables, so the copy won't have operation happen. So now the B will point to the location allocated with box represented by 67. The memory won't be freed, but the pointer will be changed from A to B. Now the pointer A will be invalid. A doesn't point to B anymore, because that ownership is transferred from A to B, or in a more rusty way, the data is moved from A to B. So if you try to print A, then it will lead to some error, like borrow of moved value A, because the data you already moved from A to B. This is what the most important ownership concept. for a heap allocated memory, once you assign it, then the data is already moved, so you can't use it again. So, but a later point of time, you can access as b value as you feeling comfortable to it. Now, because b is a box pointer, so you could use like star b operation. At this point, the data will be retrieved from b location and copied to a stack memory. So, because I marked z as a mutable variables, so we can change this data z to 55, but the original b data won't be getting modified. It is the copy which is represented by z will be modified. Now let's define another function, do magic, which take one argument c represented by box I32, and I'm just printing it. And in this case, do magic, I'm passing this b 67 to it, and under the do magic function it got printed. But interesting thing to note over here is that the ownership of b is being transferred to the do magic function as c variable. And now b will point to, the pointer will be invalidated. Now c will be pointed to the data which is represented by the 67 pointer. And in this case, once you print it, the memory allocated by c will be freed. So there is no box available which represented the data of 67. Memory will be freed at this point. So after do magic, if we want to print b, then you will get an error, because not only in the assignment operator the b2 equal to a, but also if you pass this b to another function, then the ownership is getting transferred, so you cannot access the data which is represented by in the past. Like if you create a name variable which contains the string data, this capital string type is responsible for allocating the string data inside heap. This is not a stack allocated memory, this is a heap. So all the ownership concept will be applicable to here. For example, if I declare an employee name which equal to SN name, now name is no more valid after this assignment. Now employee name will point to John, and because it is a mutable variable, we can append some additional data to it. And if you print employee name, then there is no problem. Employee name John Doe will be printed in the right hand side. But if you try to print name, then it will lead to error, because the name is invalidated in this assignment stage. So this ownership concept will be applicable to all the heap allocated structure or data type. Now let's create a employee which contain two fields, name and role. This is a struct. Struct you can define either outside of the main function, that is what the traditional, that is the recommended way, but inside also for demonstration purpose you can create the struct. So only after that you can able to access it. So I have created an instance of employee, and in this line I am destructuring the name and role from the employee. In the left hand side, your name will be pointed to emp.name and role will be pointed to emp.role. But one important thing to note over here is that before role I use a ref keyword. That means role will be pointing to this employee.role. So that is just a reference will be pointed. But wherever in this case of name, the ownership will be transferred. So you can access name and role after that thing, but you can't access emp.name. emp.role you can access. So name you can print, role you can print. There is no problem with that. So, but emp.name you can't print because the ownership is being transferred to the name. emp.name doesn't even pointing to the proper data. But role, using this role variable or emp role, you can point because you are just getting the reference of it. Now let's discuss about borrowing concept. Borrowing concept also will not deals with the stack allocated memory. For example, primitive types, for example, integers, floating point number, they already copied the data. But whenever the heap allocated memory, the ownership is transferred. For example, if you don't want to transfer the ownership, you can also only pass this address to it so that they can be acted upon or read only or write, both you can do by passing this reference or this reference or address location to another function or another variable. Let's see that how this borrowing works. So we have defined a name variable which is of string type, and we define a function hello which takes one argument name. The interesting thing to note here is that ampersand string. So ampersand is represented as a reference or a pointer or the location to the actually heap allocated memory. So whenever you are trying to pass this variable to it, you are not passing this actually data to it. So you are passing a pointer to the data. So in this case, the memory won't be freed after this hello would be completed execution. It will just having a immutable reference and just print the data. After it is done, the control will go to the main function. So the memory allocation and deallocation will still remain with the main function, not with the hello function. So you can call hello and you can still access after this hello function. But if you don't use ampersand, the ownership will be transferred and you cannot access after that line. But this is not a borrowing. You just borrow for some of your purpose, and once you use it, you will return that control back to the calling function. This is an immutable reference where you can only read only the function hello can have only read only access. Similar to read only access, you could create a mutable variable name, and we define another function which takes one argument name. But if you notice over here, the difference is ampersand string in this hello one, and here ampersand mute space string. So for example, for mutable reference, you have to use ampersand mute. And once you get that using ampersand mute operation, you don't need to give ampersand in name inside here. So you can still use the name variable as it is, and you can call all the mutable string functions or methods to modify the data. So here I am appending the last name. So similarly, in the calling also you have to use ampersand mute name. So there are three differences. In this variable name, you have to give the mute keyword to make it mutable, and you have to reference, you have to pass using ampersand mute. And inside the function signature also, you have to give ampersand mute. So in this case also, borrowing happened, but mutable borrow. Mutable borrow is can able to modify or update the data, whereas the immutable borrow can able to only read only have access. And after that, you can print the data, still you can access. It is not ownership transferred, so the control will remain with the main function. And after this println executed completed, the memory allocated for the name in the heap will be freed. So if you want, you can create any number of variables, any number of immutable variables, for example, name1, name2, and so on, which will point to an immutable reference. But you can create only one mutable reference at one time. But the important thing that if you want to use mutable reference, the order is important. So say if you want to access this immutable name1, after this mutable access, then it will throw an error. If you want to read before that, there is no problem. Okay, but if you want to use after this, it will complain. So you should not mix and match between immutable and mutable reference, because in this name one is still pointing to the profile suddenly first name and last name. But if you are getting a mutable reference, there may be possibility that you want to update or change this data. So name one will be having inconsistent data. Just to avoid having the undefined behavior or some kind of undefined use cases, Rust compiler itself is not happy about it. So you can access name3 as it is. There is no problem. And you can update the data to it. Before I wrap up today's video, I would like to give a big thank you to Rust by Example Books. Most of my examples are derived from this book. I'll give this link for this book in the description below. Thank you for watching. Have a good day ahead. Bye-bye.